This is the start of Chapter 7, sampling, survey sampling and inference. This is section 7.1. We're going to be talking about learning about the world through surveys. So most of us have at some point or another been asked to complete a survey or a poll, whether it's a phone call, someone coming up to us. They're one of the most common applications of statistics. News shows, newspapers frequently are reporting reports of surveys. And so we're going to be considering a couple things about surveys. One, can we generalize the results of a survey from some sample of people to a larger group, or which we will call our population? And the answer will be yes, if the people who participate in the survey are chosen in such a way that they are representative of the population. And the second question we want to know is, can we quantify how far away our estimate is likely to be from the actual proportion that we're looking at? And again, we're going to find this to be true, that we can find out how far away our estimate will be. So this chapter is a pivotal point in the course. We'll need to use data summary techniques from Chapter 2. Remember, in Chapter 2, we looked at whether we were looking at categorical or numerical variables and how to summarize data, whether we're using the mean or proportion. We'll also be using probability from Chapter 5 and the information we learned about the normal distribution from Chapter 6 in order to generalize information about a sample to the larger group. So recall that from Chapter 1, a sample is a subset of our population, and the population includes every person or object of interest. One of the primary goals of statistics is to learn something about a population based on what we observe in our sample. Whenever we draw a conclusion about populations based on observations from a sample, we are making an inference. And so this, at this point in the course, is really when we're starting to learn about statistical inference. Previously in chapters like 1, 2, and 3, we were really doing descriptive statistics, and now we're moving into the idea of statistical inference. We'll be continuing this for 7, 8, and 9, chapters 7, 8, and 9. When we make an inference, this is important. We can never be absolutely certain of our conclusion, but we can measure how certain or uncertain we are. So let's take a quick look at what we're talking about. So let's use this for an example. Imagine that we wanted to know something about the population of students at GCC. For example, maybe we want to know what proportion of students at GCC are full-time students. But we didn't have a way to actually ask every student this question. So instead, we took a sample. And so you can see the sample here outlined in red. And we just used the sample students that are in our class. And in the semester that I'm doing this in, I had a sample size of 15, n equals 15. So I asked these students here in my sample, full-time or not, and I find out that 45%, or let's say a third of them, or 33% are full-time. And so what we want to know is, can we use this estimate from our sample to talk about the whole population? Is 33% of the all of GCC's population full-time? And so are we close on this estimate? How can we generalize this estimate? And these are all questions we're going to be looking at in section 7.1. So we need to talk a little bit about some notation and things like that. So here's another example. A researcher asked a very small population whether they preferred stars or flowers. A second researcher decides that he doesn't have enough time to ask everyone in the population. So you can see my whole population here in the big circle. And so instead, this researcher is going to take a sample of the population. So here's a sample. He just grabbed these people, and now he's going to ask them whether they prefer stars or flowers, and then see if he can, to get an estimate for the population. So we're going to fill in this table. It won't fit on with my picture, so there's going to be a little bit of possible scrolling, but you can look at your picture while you're watching the video. So our population size is going to be represented by the capital N, and that's everybody in the big circle. So it's including the people in the small circle, everybody inside of this red circle. So if we count up all the stars and flowers all together, our population, you'll see, is 30. The proportion, now remember, proportion can be written as a fraction. It's going to be the number of things we're interested in over the total number, the proportion of the population that chooses stars. So again, in the red circle, we're going to count up all the stars, and that turns out to be 20 out of the 30 people in the population prefer stars. So that's we can change that to a decimal to look at it. So those are two ways you can show a proportion. The proportion that chose flowers. So again, we're going to be counting in the big red circle. So there's 10 people who chose flowers, and that's the same as 0.33. Okay. So the proportion for the population is represented by P. Okay, so now we'll start looking at the information about the sample. The sample are included in the small circle. And so in the small circle, we have 8 people. And the proportion of the sample that choose stars, so again, we're looking at the stars in the small circle, that's 6/8. So when we're talking about the sample, we want to notice that our symbol is P hat. That represents the proportion. And that is 0.75. And the proportion of the sample that chose flowers, again, we're using a P hat because we're talking about our sample, is going to be 2/8. A census is a survey in which every member of the population is measured. So a census is when you're able to ask every single person in the population the question. The two proportions calculated on the left are called parameters. And the parameters is a numerical value that characterizes the population. Oops. So, over a parameter goes with population. So we can remember that because parameter starts with P and population starts with P. Typically, parameters are unknown. And that is why we are doing the survey to begin with. And so typically we wouldn't be able to actually find the parameter. We would only have our estimate of based on our sample. But these over here are our parameters. So the US performs a census every 10 years, and the results of the census are used to determine how many congressional seats each state gets to distribute federal funds to local, state, and tribal governments, and to make planning decisions about communities. If we could always do a census, then there'd be really no need to do survey sampling. But typically, you can't always do a census. It's expensive. It's it's not always possible to get everybody. Hard to find people. It takes up a lot of time, and so much more often, surveying is done in order to get answers about a population. The two proportions we calculated on the right are called statistics. Statistics is a numerical value that characterizes an aspect of your sample. And so just like parameter population both start with P, statistic and sample both start with S, and that is helpful. And again, the symbol that we use for a proportion that's talking about a sample proportion is P hat. So over on this side, we have our statistics. Okay, so number 4, are these statistics close in size to parameters we calculated for the population? In other words, would these statistics do a good job estimating the parameters? So in our example, they're not too far off, but this is, of course, one of the main questions we'll want to be asking. Statistics are sometimes called estimators, and the numbers that result are the estimates. So for example, the proportion of people in the above sample that prefer stars is called our estimator, and the result, 75%, is the estimate of the people who prefer stars. Okay, so this example is not just, it is unrealistic because typically we wouldn't know the actual value of the parameter. So many times in this chapter, while we're learning about estimating, we are going to know the value of the parameter so we can see how is our estimate behaving compared to our parameter. But in real life, we don't know the parameter, we only know the estimate. Of course, because again, we wouldn't need to calculate a statistic if we already knew the parameter. So in general, statistics are knowable and parameters are unknown. Okay, so this summary table is very helpful to refer to when we're talking about representing our parameters and statistics with notation. So this side here is our statistic side of the chart, okay? And so these are all the notation we would use to talk about statistics. So X bar is when we're talking about a sample mean. S is a sample standard deviation. These are really going to come into play more in chapter 9. P hat, this is what we're doing in chapter 7 and chapter 8, is our sample proportion. On the other side of the table, over here, we have our parameters. This is about the population, parameter, population. This is our population mean is mu. Population standard deviation is sigma. Population variance, sigma squared, and population proportion is P. So again, this is what we're talking about in chapter 7. Notice that these ones are all Greek letters used to represent. Just P is the only parameter that's just the standard alphabet. Okay. Let's consider the following example. Franklin Delano Roosevelt, who was a Democrat, and Alfred Landon, a Republican, were candidates running for president in 1936. Literary Digest, a popular news magazine at the time, conducted a survey that year in an effort to predict the winner of an upcoming election. They sent surveys to more than 10 million people and found that 57% of respondents favored Landon. Roosevelt actually won the election with 63% of the vote. Okay, so is 57% a statistic or a parameter? So going back up here, we see that they surveyed 10 million people and found 57% of the respondents favored Landon. So that means this was information about a sample and it's a statistic. So our notation would be p hat equals 0.57. 63%, is this a statistic or a parameter? And this is a parameter because this is actually what happened. It said Roosevelt won the vote with 63% of the vote. So actually, let's write this down kind of as like a little chart so that we can see what happened. So for Landon, I'll just put R for Roosevelt. Okay, so the survey said 0.57 preferred were going to vote for Landon, which means that the number that we're going to vote for Roosevelt was 0.43. And actually what happened was that 0.37 voted for Landon, 37%, and 63% voted for Roosevelt. And so was Literary Digest statistic a good estimate of the corresponding parameter? And the answer is no. If you think about looking at this, that, oops, I'm missing a hat. So this isn't, oh no, it's not. I did that wrong. Wait a second, let me rewrite this. Sorry about that. Hold on. So what did I say? The parameter was that 63% voted for Roosevelt and 37% voted for Landon. So what we're looking at is this. I circled the wrong thing. That's why I got confused. Is this p hat 0.57 close to the actual parameter? And the answer was no. So no, because parameter was 37% and statistic p hat was equal to 57%. So they weren't good at estimating it. So why was that? That's an important idea. We need to think about what was going on with this survey that made it not a very good survey. What went wrong? Literary Digest sent surveys to 10 million people whose names and addresses they obtained from telephone books and vehicle registration lists. So in order to send it to an address, they had to get the list from somewhere. So they used telephone books, they used vehicle registration lists, and the people who are already reading their magazine. So this is in 1936, and not everybody owned a vehicle, not everybody had a telephone, and certainly not everybody would be a Literary Digest reader. So one thing to think about is that they were probably overrepresenting the wealthy in their survey. And wealthy people in 1936 tended to favor the Republican vote. And so the people responding, wealthy, let's see, tended to favor Republican. Okay, so they overrepresented that in the sample, and so they were probably getting more people saying, "Oh yeah, I'm going to vote for Landon," than actually were. So it's really important to think about who's being included in the sample. And although Literary Digest mailed the survey to 10 million people, another important thing is that not everyone responded. In fact, 2.4 million people responded. And how do you think that influenced the results? So again, just think about it at your house when you get a letter in the mail asking you to fill out a survey. How often do you throw that out? And when don't you? When do you fill it out? Well, most of the time, people fill out surveys when they have something they want to say. They're probably unhappy. And so since Roosevelt was already the current president, so Roosevelt was current president. People who responded were probably people who were unhappy with him. Or not everybody, but more likely to be. So that brings us to talking about a couple types of bias that can come into play in a survey. So the sample used by Literary Digest was not representative of the population, so that's an important idea, because the sampling method was biased. A sampling method is considered biased if it tends to overrepresent or underrepresent certain segments of the population. So likely they overrepresented the wealthy population, which tends to produce an untrue value. The sampling method used by, oh, that's what I just said. So skipping that, how will we know if our samples are representative of our population? We need to consider sampling method used and whether the sampling method is biased. So there are other types of bias that we can talk about here. There's measurement bias. This is a result from asking questions that do not produce a true answer. So that's if the way things are worded could be one way to have measurement bias. Response bias is the people that respond to a survey may have stronger feelings about the topic than those that choose not to respond. So the fact that not everybody's always responding. Only 24% of the people returned that survey, 2.4 million out of 10 million. When reading about the results of a survey, these are questions you want to ask yourself. What percentage of the people who were asked to participate in the survey actually participated? If a large percentage didn't, refuse to participate, then we should ask why didn't they? Because we might not be representing the whole population. Do people voluntarily choose to participate? When people choose to participate, why would they be potentially different from those who did not choose to participate? Sometimes there's a bias there. Did the researcher choose the participants, and if so, what types of people were included in the survey? Which ones were left out? So we just talked about that they chose people based on these lists, but they wouldn't have had lists of people who didn't own a telephone or a car. And so they're tending to leave out some of the population. Were the participants able to respond anonymously? So that's a key one, like if someone comes up to you face to face and asks you questions, oftentimes people don't want to respond because a question or answer might feel embarrassing, and so people might lie or choose not to participate. So our goal is to find a sample that is representative of the population that we want to know about, with as little bias as possible. The best way to do this is to ensure that everyone in the population has an equal chance of being chosen, and this comes from a simple random sampling. So you're going to hear a lot about SRS, simple random sampling. This ensures that every member of the population has the same chance to be chosen, and that every sample of a given size has an equal chance to be chosen. So in simple random sampling, subjects are drawn from the population at random and without replacement. Without replacement means that once the subject is chosen, they cannot be selected again. And if this is accomplished when statistics are calculated from our samples, the statistics calculated will produce unbiased estimates for the corresponding population parameters. In other words, our p-hat will be unbiased estimate of p. P-hat being our sample statistic for proportion, and p being our population parameter for proportion. We will also be able to measure the sample's precision and how far off we expect our estimates to be.